Okay, it's 5:30, so let's go ahead and get started today. All right, evening everybody. How's everybody doing today? Good, good, great. So I know on Monday I promised you guys that I'd have the midterms graded by today. So I don't have it yet. So obviously check the Canvas, you'll probably see that. So I apologize for that. You know, usually what I try to get back, you know, graded things to you guys within a week after it's due. But you know, today I kind of had a lot of things come up because I had a big research proposal that was due today. So I apologize, but I did get started a little bit on it. So I graded, I think maybe like eight of them before the lecture today. But I'll have them all done by tomorrow for sure, because the proposal stuff is basically most of it's out of the way, and I'll be free tomorrow. So I'll have your midterms graded by tomorrow, and I'll send an announcement about, you know, the average and everything about that tomorrow too. Okay. Okay, so the plan for today is we're going to finish up our lecture notes on the strong and the weak form. So we don't have too much left, so I think probably we'll be able to finish it and maybe start our next lecture notes on finite element forms, which is kind of the sequel to, you know, how do we turn a weak form of boundary value problem into a finite element problem. Okay. But before we get started, are there any questions on either what we covered last week or the activity that's due this Sunday, or just, you know, anything in general that I can answer? Okay. All right, so let's go ahead and get started. Okay, so where we left off last week, I think we had just finished deriving the weak form for a 1D elasticity problem. Okay. And if you remember, you know, the way that we obtained this was we took our differential equation, which you know, governs the displacement of in this case, a truss element in one dimension. And then we multiply it by a weighting function. We integrated it. We performed integration by parts, and then we worked with a lot of the terms, and we end up with this kind of long expression here. Okay? And so I'm going to write a slightly more general version over what I did last time, just so that you can apply this to almost any problem. Okay? Okay? And so first we start out with this term W at gamma H times T bar times A at gamma H. Okay. And so this is a new thing right here. Okay. And so, you know, I'm using this term gamma H right here to denote the location of the Neumann boundaries. Okay. Okay. So I think at the end of last lecture, I just put 0 right there because the example problem that we were doing had the Neumann condition at x equals to 0. But here I'm just making it a little more general. So you can either have your Neumann condition at x is equal to L or at x equals to 0. So you know, just making this a bit more general. Okay. And then from there, we're going to subtract. We have our balanced derivative term. Okay, so we have minus integral from 0 to L of dw dx, okay, times e times a times du dx, okay, dx, okay, plus. And so that's our, we can kind of think of this as the primary physics term, okay, so that this contains our Young's modulus and our area. Okay? And so, you know, just thinking ahead a little bit, you know, eventually what this integral right here is going to become, this is going to form the basis for our element stiffness matrix. Okay? And so if you remember, you know, from the first question on the midterm, you know, I asked you to kind of sort out different properties of in that case, it was a fluid mechanics problem, into where you would expect them to be in your global system. Okay? And so the fact that this term right here has our Young's modulus and our area, okay? And so that kind of gives us a hint that what this integral is going to turn into is that this integral is going to turn into our element stiffness matrix. Okay? Okay. And then from there we have our body force term. Okay. And so that's just the integral over the domain. So integral from 0 to L of Wx times B of x dx, that integral. Okay? And all of this is equal to 0. Okay. And so the other thing that, that was part of our weak form was our requirements on our weighting function. Okay, so remember the way that we described this was say that this form holds for all W. Okay, so remember this this symbol right here stands for all. Okay. For all W, where W at gamma U is equal to 0. Okay, and also U at gamma U is equal to U naught. Okay, and so again, I'm using this gamma notation right here to denote the boundary. In this case, gamma U is going to be the location of the Dirichlet boundary. Okay. And then just one more thing, U naught right here. This is our specified Dirichlet value. Okay. Okay. And so let's put a box around this guy. And so there's our weak form. Okay. And so at the end of lecture on Monday, we talked about you know, some of the advantages of this weak form. Okay. And so first of all, you know, one advantage that we have is that we can first look at all the derivative terms in this weak form. Okay. And so remember the strong form equation that we started with had a second derivative on u. So we had d squared u dx squared times e times a, you know, plus b of x is equal to 0. Okay. And so one of the benefits of the weak form is that we can kind of separate this derivative out. So instead of having one second order derivative term, we have two terms that are first order derivative. Okay. And what you'll see, you know, later on, actually at the end of lecture today, why this is actually really nice and is actually really important. Okay. And then the other thing that we talked about was this. Okay. And so the nice thing about the term that's circled in orange right there is that that's our Neumann boundary condition. Okay. And so for any kind of Neumann boundary condition that we have, you know, these are actually baked right into the expression. So we don't have to do anything separate with them. Kind of like what as if we would do for a strong form equation. Okay. Because remember, the strong form equation, the way that we express it is a differential equation and then all of the boundary conditions. Okay. But because our Neumann boundary condition kind of is baked right into the expression, you know, we just kind of solve for it at the same time as everyone else. Okay. And so the only thing that we have to really specify is the Dirichlet boundary conditions. Okay, so this is the weak form that we went over last time. But again, it's a little bit different just because I'm using these gammas to denote the boundary. So this is kind of general for any kind of domain. Okay, no matter where your boundary conditions are. Are there any questions on this? Okay. Okay, so let's go for some other key facts about the weak form. Okay. Okay, so the number one thing I want you to remember is the requirements on our Dirichlet boundary condition. Okay, and so wherever we have a Dirichlet boundary condition, okay, it doesn't matter what the Dirichlet value is. So the Dirichlet value can be anything. But at those locations, we have to require that our weighting function will disappear there. Okay? So I'm just going to draw two quick examples for you here. So let's say that we have a situation like this. And so say that we have a bar that looks like this. Okay? And we have a fixed condition at x is equal to 0. And so if this was our problem in question that we were solving, then our Dirichlet boundary condition here would be at x is equal to 0. And so what that means for our weighting function is that our weighting function at x is equal to 0 has to be 0. Okay? But if you had a situation that looked like this, where our fixed condition here is that x is equal to L, okay? What this tells us is that W at L has to be equal to 0, okay? So it depends on your problem. So if your problem, has a Dirichlet boundary on the left-hand side, then you would have W of 0 is equal to 0. And if your Dirichlet condition is on the right side, you have W of L is equal to 0. Okay? And this is going to get even more complicated once we get into 2 dimensions. So in 2 dimensions, we're not just going to have a left boundary and a right boundary. We're going to have an upper boundary and a lower boundary, and a left boundary and a right boundary, and all kinds of weird things. For 2D, things get really, really complicated. So I really want to make sure that at least in 1 dimension, this point kind of gets drilled into your head that wherever there's a Dirichlet boundary condition, we have to have the weighting function disappear there. Okay. All right. So the question is, can't we change our origin to make it easier? You can. For a 1D case, you can definitely change the origin such that it's always x equals 0. But again, once we get into 2 dimensions, or we won't be doing any 3-dimensional stuff. But you can imagine, in 3 dimensions, the problem is going to get worse. Whenever you have a Dirichlet boundary condition, whatever surface or whatever edge or whatever, your weighting function has to be equal to 0 there. Okay. And so I'll draw you kind of a quick, sketch of a 2D situation. Okay. And so say that we have a 2D block that looks like this. Okay. So we have kind of like a backwards L block, right? And so let's say that on this L block, we set a Dirichlet boundary condition here and here. Okay. And so if we have this being a structural problem, we can say that we have a fixed wall right here and also a fixed wall right there. Okay. And so at those locations, in this case, our weighting function is going to be a function of x and y because it's a 2D. Okay. Okay. And so W at x and y at those locations have to be 0 because those are your Dirichlet boundary conditions. Okay. So in 1D, yes, you can change the origin just so it's always equal to 0, but just kind of be aware that in 2D and 3D that might not always be possible. Right?
So you say basically because there are 2 places that the boundary condition is applied, it doesn't make any difference whichever we make the origin. Got it. Thanks.
Exactly. Yes. Yeah. And so in 3 dimensions, it can be even more complicated because you can have all different kinds of stuff too. So
yeah, I can imagine.
Yeah.
Thanks.
So this kind of general definition where you just say wherever there's a Dirichlet boundary condition, we make it W of that equals 0. This kind of works for no matter how many dimensions that you're working in. Yeah, great question though. Right. Any other questions on this? Okay. Okay. So the other key fact about the weak form kind of goes back to its name, is that even though we call it the weak form, weak doesn't imply inferior. Okay. And so the weak form and strong form are equivalent. And so if you notice, up to this point, in order to get the weak form, we did a lot of weird things. Like we multiplied by a function and we integrated, then we integrated by parts, but nothing that we did was an approximation. Okay? So all the mathematical techniques that we did were exact techniques. Okay? Okay. And so just because we're solving the weak form of a solution doesn't mean that we're getting an inferior solution or anything like that. It's just a different form of it. Okay? And so the reason this gets its name, and the reason why we call it the weak form, is because the requirements on the solution are not as strict. Okay? And so the reason it gets this name is because there's weaker continuity requirements on the solution. Okay? But it's still the same. You still get the same solution. Okay? Okay. And so if you're solving these equations exactly, this idea of continuity actually never comes into play because you're solving for an exact solution. Okay? But where this really helps you is when you're solving for approximate solutions. Okay? Okay? And this is really important because the finite element method, for as much as we're going to be studying it, it's still an approximate method, right? And so you're still doing a simulation. So you're not solving the equations exactly. You're finding an approximate solution to it. Okay? And so that's why the weak form is so powerful for finite elements, because it allows us to form a finite element solution in a much easier way than if we worked off the strong form of the solutions. And we'll see that at the end of lecture today when we learn how to take approximate solutions. So the approximate solutions we find at the end, they're not technically finite elements, but it's a building block towards that. It's a big step towards it. Okay? Okay. And so one little piece of trivia. So this is in the grand scheme of things, not too important. But if you've taken like a structural mechanics class before and you've heard of this concept of virtual work, that this whole exercise that we just did of deriving the weak form is exactly equivalent to the principle of virtual work. Okay? But if you don't know what this is, then don't worry about it because it's not that important. But if you have learned it before, then this is basically the exact process. So you can if you've taken a class with this, you can look back on your notes and you can see we arrive at the same thing. Okay. Okay. And so one more point that I want to make before we jump into heat transfer is this idea of the residual. Okay? Because what we're going to be doing at the end of class today is we're going to be solving for approximate solutions to the to our boundary value problems. Okay, and so this residual, you can kind of think of it as the error in an approximate solution. Okay? Okay. And so the way you define the residual is like this. So let's go back to kind of the strong form of the equations. Okay. So in the strong form, we had the following. So we had d dx of e a du dx, okay, plus b of x is equal to 0. Okay. Right. And so if you had an exact solution to this equation, so we had a perfect u, right? And so if we plug that u into this equation, it would be perfectly satisfied. So we plug in u, we'd multiply by EA, take the derivative, add b, this equation would be satisfied. Okay. But if we had an approximate u, so let's say that we had, u approximate, maybe say that we get this from like a finite element method, okay, and we plug this in, then this is not going to be equal to 0, right? It's going to be something else because the solution that we found is only approximate, it's not exact. Okay? And so this function is actually going to be the form for our residual. Okay? And so basically we're going to replace the 0 right here with a function r of x. And so this function r of x right here, this is our residual. Okay. And so, the residual, obviously, if we have an exact solution like we have right here, this residual is going to be equal to 0 because it's an exact solution. But for cases where we don't have an exact solution, we have an approximate solution instead, this residual is going to be not equal to 0. Okay. And we'll define this a lot better once we do an example later on. But I just kind of want just to introduce the idea before we jump into heat transfer. Okay. Okay. Are there any questions on this? Okay. Okay. And so that's the strong and weak form for elasticity. And so now let's do the same exercise for heat conduction. Okay. And so let's start with the strong form. So when first we have the strong form for heat conduction. Okay. And we're still in 1D. Okay. Okay. All right. And so, before we actually get started with this, I'll give a little caveat that when you're in one dimension, mathematically, an elasticity problem and heat conduction are exactly the same thing. So, I'm going to write a differential equation here, and you'll say that it's exactly the same thing. I just changed some of the letters around. Okay. I don't know if you guys can hear, but our neighbors below us got a pug puppy recently. It's very cute, but it also barks a lot sometimes. Okay, and so, mathematically, it's going to be the same. So actually, over the next lecture, for the rest of lecture today, we're just going to be kind of repeating a lot of the things that we did last lecture. Okay, but where this is going to be a difference is going to be, there's going to be a difference in 2D. Okay. Okay. Because in 2D, our solution variables are actually going to change. Okay, because for elasticity, remember we're solving for displacement. Okay. Okay. And what we know about displacement is that it's a vector quantity. Okay. And so once we move into 2D, we actually need to solve two equations at the same time. So we need to solve for the x displacement, an equation for that, and then we need to solve for an equation for the y displacement. So it kind of becomes double trouble in 2D. But for heat conduction, what we're solving for is actually a temperature. And so temperature, luckily, is a scalar value. Okay. And so when we move to 2D for heat conduction, when we move to 2D, actually, we're going to reverse it. So the first thing we're going to do in 2D is heat conduction, just because we're only solving for just one variable, which is the temperature, because it's a scalar quantity. Okay. Okay. So I just want to kind of make that note before we get started. Okay? But schematically, it looks like this. So let's say that we have we'll call it a bar again. Okay? And on the left right here, instead of having a fixed displacement, we're instead going to have a fixed temperature. Okay? And so let's say that temperature is T naught. Okay? And then on the right over here, let's say that we have some heat flux. Okay? And so instead of a stress, we're going to be applying a heat flux. We'll give this a symbol Q bar. Okay. And then over the top of the bar, let's say that we have some kind of a heating. Okay. Okay. And we'll give this the function S. Okay. And so we'll say that S of X is the heating that the bar experiences per unit length. Okay. Okay, and then what we're solving for in these heat transfer problems is we want to solve for the temperature distribution in the bar. Okay. And so our goal with heat transfer problems is to find a function T of X that describes how the temperature evolves in the bar. Okay. All right, so let's talk properties. So in elasticity, we had properties like the Young's modulus and the area. And so the equivalent for those in heat transfer are going to be the thermal conductivity. Okay. So we'll give that the symbol K. Okay. How long has it been since everyone's taken a heat transfer course? Hopefully not too long. But at the same time, it doesn't matter because we're going to be solving math problems. It's just heat transfer gives us a nice context because it's relatively simple compared to a lot of other problems. Okay. 12 years. Okay, that's fine. We're going to be solving the math problems again. 14 years. All right. Yeah, no problem. No problem. Okay. And so just like in elasticity problems, we're going to have the cross-sectional area. So that's going to be another important parameter. Okay. Okay. And so what I'm going to do on the next page is I'm going to give you the strong form of the equations. Okay. I'm not going to derive it like last time, just because the derivation kind of follows the same process. But what you'll see is that the form of the equation is exactly the same as what we did before. Okay. Okay. Any questions on this? Okay. Okay, so let's write out the strong form of the equation. So if you go through the whole, you break it up into tiny slices. And in this case, instead of doing a force balance, you do an energy balance. You do all that, yada yada, and then you get the following. Okay. So you can get d dx of k a dt dx plus s of x is equal to 0. Okay. Right. So you can see the differential equation is exactly the same as our elasticity case. So the only difference is that instead of E, we have K, right? So this is where E went before. Okay. Instead of U, which is our displacement, we have T. Okay. And instead of B, our body force, we have S, which is our heating per unit length. And so the letters are different, but mathematically it's still exactly the same. All right, let's talk boundary conditions. So first we have our Dirichlet boundary conditions. Okay. And so we're going to define it by this. Okay. Right. And so remember, I'm still using this gamma notation here. So this gamma notation just simply states the location of the Dirichlet boundary conditions. Okay. And so we can say that T at gamma U is equal to T naught. And for this diagram right here, since I drew the fixed temperature on the left, what this tells us is that TU is equal to 0, just for this problem. So, in other problems, your gamma U will be different, but I just want to just show you just kind of a situation that I drew there. Okay. And so we also have our Neumann boundary conditions. Okay. And so the way that we denote that is the following. Okay, so we take the dot product of the normal vector times k dt dx. Okay, and the location for this is going to be x is equal to gamma h. All right, and this can be minus q bar. Okay, and so this n dot right here, all this does is just this just changes the sign depending on what surface that you're on. And so, you know, if you're on the left-hand side, you know, our normal vector would look like this, and on the right-hand side, our normal vector would look like that, okay? And so depending on, I think if you're on the left-hand side, then this is gonna be a negative, okay? And then if you're on the right-hand side, this is gonna be a positive right here, okay? Because remember, this respects the positive x direction, okay? And so this right here, this is the strong form of our heat conduction problem. Okay? And so just like we saw in elasticity, so it consists of a governing differential equation. So we have a differential equation for T, and then we have boundary conditions which describe the solution at the boundary. Okay? On the right side of the equal sign, this is a Q right here. Yeah, let me draw a bit more clear. It should be minus Q. And so that Q bar, that's our heat flux that's on the right. So that corresponds to what I have in red right here. Yeah. So it's just our Neumann boundary conditions. All right. Any questions on this? Okay. And so now that we have the strong form, we're ready to derive the weak form. So this is kind of nice because, you know, the derivation of a weak form is, it's always nice to view a couple times just because it's you know, it is kind of a strange thing. Okay, and so the way that we're going to get this is the same process that we went through for the elasticity. Okay, and so what we're going to do is we're going to multiply by a weighting function and then integrate over the domain. And then after we integrate, we'll be able to do integration by parts to balance the derivatives. Okay. And so later on, you know, once we're doing finite element problems in 2D, you know, and even in 3D too, you know, we're going to follow this exact same process. But the process of doing integration by parts in 2D is a little bit different. So we're going to have to rely on something called a Green's theorem. But besides that, you know, the idea of the weak form is always the same. So, you know, always with the weak form, you're trying to, you know, reduce the total order of the derivatives, so that when you apply an approximate solution, it's a lot easier to do so. Okay. Okay, so let's go ahead and get rolling on this. Okay. Okay, so if we take our you know, differential equation that we have at the top here, I'm going to multiply it by w of x and then integrate. Okay. And so if we do that, we get the following. So we have integral from 0 to L of w of x, okay, times d dx of k a dt dx, okay, plus s of x, okay, and this is dx, and all this is equal to 0, okay. Where once again, remember, you know, after we've done this, we have to require that w of x vanishes on our essential boundary. Okay. Okay. And so just like we did in elasticity, you know, we look at the derivatives here. We see that w has 0, while t has 2. Okay, so we're going to apply integration by parts to balance the derivatives. And so if we do that, and then we get our extra terms, we get the following. Okay? So we get W times Ka times dt dx. Okay? And this is evaluated from 0 to L. And so that's kind of the extra term that pops out from integration by parts. But again, remember, this one is going to turn into our Neumann boundary conditions. Okay, and then we're going to subtract our integral from 0 to L times dw dx times Ka times dt dx. Okay, and so now notice that we have two first derivatives instead of a second derivative term. Okay, plus our body force term. So in this case, our body heating term. Okay? So W of x, S of x, dx, and all this is equal to 0. Okay. Right. And so once again, you know, when we evaluate this guy, so this guy is evaluated at both of our boundaries. So you can see that we're going to evaluate this at x equal to 0 and x equal to L. Okay. Okay. And so when we evaluate this guy at both boundaries, you know, we're going to have two terms. So we're going to have one term at x equal to L and another term at x equal to 0. You know, one of these is going to disappear because of our requirement on Wx. Okay. I should say at least one will disappear. And so the reason for that is, you know, whenever we do a finite element problem, we always have to have at least one Dirichlet boundary condition. Okay? Okay? So this is 1 plus right here. Okay. So it's not onet, it's 1 plus. So, you know, we have to have at least one, but, you know, what we'll see in heat transfer is that we can also have two Dirichlet boundary conditions for a 1D. Okay. All right. And so when we put this all together, we can form kind of the formal form for the weak form. Okay. Okay. Any questions before we get to that? Okay. Okay. And so if we finish writing it out, we'll get the following. So I'm going to start with the derivative terms. We have an integral from 0 to L of dw dx of Ka du dx dx. Okay. And so this is equal to integral from 0 to L of wx s of x. Okay. And so you notice I moved the derivative term over to one side of the equation. And that this will actually be more convenient once we're actually applying, you know, our finite element form. Okay. So then we have our body forcing term or our body heating term. Okay. Then we have plus our Neumann boundary condition term. So this is W times Ka times dt dx. Okay. And this is evaluated if x is equal to x or x is equal to gamma h. Where gamma h, remember, is our Neumann boundary condition. And this is for all W, with W of gamma u is equal to 0, and u at gamma u is equal to t, no, okay. Or I should say t at gamma u, sorry. All these should be t's. Okay. All right. So that's the full weak form for heat conduction. Okay. And so mathematically, you know, this looks the same as elasticity. So I know that the parameters are different, but we have the same derivatives in the same place and the same functions in the same place everywhere else. Okay. And so this, you know, this form right here mathematically is equivalent to elasticity, but once we get into 2D, you know, that's going to change. But for now, you know, elasticity and heat transfer have the same forms. Okay. Okay. And so let's just do a quick example just to show how you can solve for these solutions. So first, let's solve. I'm going to do an example to solve for the strong form, and then after I'm going to do a solution for the weak form. Okay, and so say that we have a bar that looks like this. 1D is kind of boring because, you know, there's only so many shapes you can do with 1D. And when I say there's only so many shapes, I mean there's only one. Okay, and so we have a Dirichlet boundary condition on the left-hand side, so we can say that the temperature there is going to be equal to 25 degrees C. Okay. All right, and so in this case, we're going to have a heating. Okay, so our heating is going to be given by this function. It's going to be x squared over 5. Okay. And then on the right-hand side, we're going to say that this surface here is adiabatic. Okay. And so all that basically means is that we're going to say our heat flux is equal to 0 here. Okay. And so when we plug in this, plug into our equations, we just say that Q bar is equal to 0. Okay. All right, so let's define some properties. Okay. So we can say our thermal conductivity is going to be 2 joules per meter degrees Celsius seconds. Okay. And then our area is 0.5 meters squared. Okay. And our length is equal to 5 meters. Okay. And so we're going to use this information to solve for the strong form of the solution. Okay. Or we're going to solve the strong form for the exact solution. That's what I meant. Any questions on this? Okay. Okay, so let's start with our strong form solution. Okay. And so, you know, our strong form is given by this. We have ddx of Ka dt dx, okay, plus S of x is equal to 0. Okay. And so let's plug in K, A, and S of x. Okay. Right. And so we do that, we get d squared t dx squared. Okay. And so our two properties are going to cancel out. So we have 2 times 0.5, so that's just going to be equal to 1. And so that's why we just have d squared t dx squared. Okay. And then our s is going to be plus x squared over 5. Okay. S equal to 0. Okay. And just so we can integrate this easily, let's move this x squared over 5 to the other side. So we have d squared t dx squared is equal to minus x squared over 5. Okay. And now that we're in this form, we can just simply integrate to find the solution. Okay. And so let's go ahead and do that. So if we perform this integration right here, then we, on the left-hand side right there, we get just simply dt dx. Okay. And on the right-hand side, we have minus x squared, x cubed, excuse me, minus x cubed over 15. Okay. plus C1, right? Remember, since we're performing an indefinite integral here, we have to add the constant. And so if we integrate this again, okay, and then what we get is T of x is equal to minus x to the fourth all over 60 plus C1x plus C2. Okay, so there's our general solution. And then to solve for C1 and C2, we're going to apply our boundary conditions. Okay. Okay. And so let me apply our Dirichlet boundary condition first, just because this is pretty easy. And so our Dirichlet boundary condition was simply T of 0 is equal to 25. Okay. And so we're going to take our expression here and plug in 0 for everything. So we have minus 0 to the fourth over 60 plus C1 times 0, okay, plus C2. Okay. And so since these guys are 0, they're just going to cancel out. So we get C2 is equal to 25. Okay. All right, any questions on this example so far? Let me turn on the light back. Days are getting shorter. I keep forgetting that. Okay, so that's the first boundary condition. So let's apply our other boundary condition. Okay. And so on the right-hand side, we have an adiabatic condition. Okay, and so what that tells us is that k times dt dx. Okay, at x is equal to 5. Okay, because it's at the right-hand side of our domain. Okay, so normally this is equal to q bar, but in this case, since we have an adiabatic surface, we can just say that it's equal to 0. Okay, all right. So let's plug this in. So we have k times dt dx, and so our dt dx in this case was minus x cubed over 15 plus c1. Okay, this is equal to 0. So let's divide both sides by k, get rid of that. Okay, and then plug in x is equal to 5 for our only value of x here, which is right there. Okay, and so we have minus 5 cubed all over 15 plus c1 is equal to 0. So what that tells us is that c1 is equal to 125 over 15. Simplify a little bit. This is 25 over 3. Okay, and so if we plug in C1, C2, then we can get our T of x. Our T of x is going to be equal to minus x to the fourth all over 60 plus 25 over 3x plus 25. Okay. All right. And so that's just a strong form of the solution. So, this is just kind of ODE stuff. So, and luckily in these cases, the ODEs don't get too complex. So most of the time we can just simply integrate. Okay. And again, since we didn't perform any approximations, we didn't do any assumptions, this solution right here is exact. Okay. All right. Any questions on this? Okay. Okay, so that's strong, exact solutions to the strong forms, right? And so that'd be great if this were, a class on differential equations. But because this is a class on finite elements, we're going to take this in a different direction, not the next step, but just a different direction. Okay. And so what I'm going to give you right now until the end of class is just kind of a primer on how to solve for approximate solutions to the weak forms. And so what we're going to use here is kind of it's almost like a prelude to how, we can turn the weak form into a finite element problem. Okay. All right, so the key word in this is approximate, right? So approximate basically means that we're not going to get the exact solution. Okay? Okay. And so there's a lot of ways that you can approximate something, right? So, you know, one way to approximate something is just to guess, right? So you can just take, you know, if I can say, you know, give me T of X, right? So give me the temperature, you can say, you know, I approximate this, close my eyes, it might look like that, right? So that's one way you can approximate. But as you can imagine, you know, there's no, you know, one way to approximate, and there's levels to it. So there's good ways to approximate something, and then there's very bad ways to approximate. So closing your eyes and just scribbling on a paper obviously is a very bad way to approximate. Okay? And so we're going to go over kind of a good way to approximate that kind of, you know, it kind of forms the basis for our finite elements. Okay? And this kind of goes back to our, you know, if you remember from the very first day of class, you know, we talked about, you know, what was kind of the general finite element method, you know, what are the general steps? And so the first step, first of all, is that you have to discretize. And so you have to break up your domain into a mesh, okay? And then the second step, which, you know, I've kind of been glossing over all this time, is to assume a form of the solution. Okay? And so, you know, one way that we're going to form an approximate solution is to first assume what the solution looks like. Okay. And so I'll put looks like in quotes right here because, you know, what we're going to assume is that our solution follows, you know, it belongs to a certain class of functions. Okay? And then, you know, within that class of functions, then we're going to solve for what is the best function in this class that will solve this problem. Okay. Okay. And so let me give you an example here. Okay. And so let's say that you know, we're going to assume that our function or solution is going to be a quadratic function. Okay. And so it belongs to the class of solutions of it belongs to the class of functions where it's going to be any quadratic. Okay. And so if we write kind of the most general quadratic function, it would look like this. Okay. Right. So the most general quadratic function that we can come up with is a naught, where a naught right here is our constant term, and then we have our linear terms. We have a1x, and then we have our second order polynomial term, which is a2x squared. Okay. And so the a's here are important. Okay. And so these a's right now are unknown coefficients. Okay. Okay. And so, you know, what we're going to do is we're going to take this this form and then plug it into our weak form, and then we're going to solve for these coefficients, or basically we're going to solve for the you know, the best values for these coefficients to get us as close to the solution as possible. make approximate solution as close to exact as possible. That ended up being a lot more writing than I thought it was going to be. Okay. Okay, and so, you know, I'm going to walk you through the process of doing that in a bit. Okay. But one more thing before we jump into it is that, remember, in our weak form solutions, we also have another function w of x, right? And so that's our weighting function. And so one rule that we're going to have for our finite element solutions is that our weighting function here follows the exact same form as our solution. Okay? So if our solution, we assume it to be a quadratic, then our weighting function also has to be a quadratic function. Okay. Okay, but these guys have their own coefficients. Okay. So we'll call them B0, B1, B2. Okay. Okay. Right. And so whatever form that we choose for our solution, you know, we're going to choose the same form for our weighting function. Okay. Okay. So any questions on this before I move on with the example? Okay. All right. So actually, you know, before we actually plug these into the equations, you know, we have to enforce our Dirichlet boundary conditions. Okay. Because remember what we said about the Dirichlet boundary condition. So, you know, wherever there's a Dirichlet boundary condition, then our weighting function has to be 0 at those locations. Okay? And so this will actually help us solve for some of the coefficients. And so I'm going to take basically the situation from our previous example. Okay. So remember in our previous example, we had a Dirichlet boundary condition of 25 at x equal to 0. Okay. And so we wrote that Dirichlet boundary condition like this. So we said that t of 0 is equal to 25. Okay. And so if we set this equal to our approximate solution on the previous page, okay, we can say that this is equal to a0 plus a1 times 0 plus a2 times 0 squared. Okay. And so in other words, we have a0 is equal to 25. Okay. And so that's one of the coefficients, so that's good. Okay. And then by that same token, you know, we know that w of 0 also has to equal 0, because remember, wherever we have a Dirichlet boundary condition, our weighting function has to disappear. And so this is going to be equal to b0 plus b1 times 0 plus b2 times 0 squared. Okay. And this tells us that b0 is equal to 0. Okay. And so right off the bat, just by applying our Dirichlet boundary conditions, we've solved for 2 of the coefficients. Okay. Okay. And so with these guys solved for, you know, we're ready to plug in. Okay. And so let's go ahead and do that. Okay. And so just to kind of remind you, this is our weak form here. So our weak form is integral from 0 to L of dw dx, ka dt dx, okay, dx is equal to integral from 0 to L of w of x, s of x dx, plus our Neumann boundary condition term. Okay. 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 And so I'm going to make a really quick simplification. And so remember, for this particular problem, our Neumann boundary condition was 0. Okay. Okay. And remember, that's because in the problem we assume that there's no heat flux at x is equal to L. But this is not always the case. So remember, when you're solving for approximate solutions, make sure that you apply the correct Neumann boundary conditions. It's just that for this particular problem, we had no heat flux. Okay. So for just this particular problem, but for other ones, you might have something. Especially if you're going to apply this for elasticity, you might have a stress on one end of the of your bar. Okay, so once we cancel that out, we're going to plug in for everywhere that we see a W, okay, and we're plugging everywhere that we see a T. So we only see a T, I think, right here. Okay. And then obviously, we have S of X, and so we can just go ahead and throw that into this expression as well. Okay. All right. Any questions on this before I continue on with the solution? Okay. Okay, so it's going to be a bit of algebra, but stay with me. So our first term is going to be integral from 0 to 5 because our L is equal to 5. And this first term we have a dw dx, and so the derivative of that is going to be b1 plus 2b2x. Okay, and then next we're going to multiply that by dt dx, which is a1 plus 2a2x. Okay, dx, right? So remember, k and a in this particular problem cancel out because I think k was 2 and a was 0.5. Okay. And then from this, we're going to subtract the integral from 0 to 5 of w of x. And so this is just w, not dw dx. So this is going to be b1 x plus b2 x squared. Okay. And this can be x squared over 5. Okay, dx is equal to 0. Okay. All right. And so, you can, do a lot of the algebra on this, but let me just give you a note about what I did. Okay. So what I'm going to do is I'm going to separate this guy out into an integral that has b1 and an integral that has b2. And so all I'm going to do is basically just distribute this this quantity with the a's through, and then just have one integral with a b and one integral with an a. Okay? And so what that gives us is b1, okay, times integral from 0 to 5. Remember, the b's and the a's are just constant coefficients. So if they're by itself, we can pull it out of the integral. Okay? a1 plus 2 a2x dx. Okay. Plus 2b2 integral from 0 to 5 of a1x plus 2a2x squared dx. Okay. And then we're going to subtract. We're going to separate this guy out into b1 and b2 integrals as well. So we're going to subtract b1 integral from 0 to 5 of x cubed. X cubed over 5 dx, okay, minus integral from 0 to 5 b2 x to the 4th over 5 equal to 0. Okay, and then just like the other ones, we can pull this guy out of the integral. Okay, so we have a b2 out in front. It should be 0. And so now that we have these integrals, what we can do from here is we can combine the integrals that involve b1. Okay, and so that's going to be this guy and this guy. And then we can combine the integrals that involve b2, which are going to be this guy and this guy. Okay. Okay. All right, any questions on this? Okay. Okay, so then if we combine them, we get the following. So we get B1 times the quantity, integral from 0 to 5, A1 plus 2A2x minus x cubed over 5 dx plus B2 integral from 0 to 5, 2A1x plus 4A2x squared minus x to the 4th over 5, okay, dx. Okay. And all this is equal to 0. Right? And so once we get to this point, we can finally perform the integration. Okay. And so we get B1 times A1x plus A2x squared plus, oh, minus x to the 4th over 20 plus B2, well, this is a value from 0 to 5, B2 times A1x squared plus 4 over 3 A2x cubed minus x to the 5th over 25. Okay. It's also evaluated from 0 to 5. Okay. And all this is equal to 0. Right? And then if we perform these integrations, we get the following. We get B1 times 5A1 plus 25A2, okay, minus 31.25, right, plus B2 times 25A1 plus 500 over 3, A2 minus 125. And all this is equal to 0. Okay. All right. So a lot of algebra and a lot of integration, but this is what you're going to end up with. Okay. All right. Any questions on this so far? Probably still people are writing. Probably people are still writing it down. So I'll give 1 more minute. It is hard to do on virtual because in the classroom I can see people still writing things down, so it's easy to know when to pick up. But in virtual it's hard to see that. All right. So the question is, how did I know the bounds were from 0 to 5? And so the bounds were from 0 to 5 in this particular case because I'm redoing the example that we did here. And so in this example, our length here was 5. And so normally you would integrate from 0 to L, but in this particular problem, the length was 5. So that's why we're integrating from 0 to 5. Yep. Yeah, so if you're applying this for another problem, make sure that you choose the correct length. Okay. All right, so at this point, we're, we have to solve the system for A1, A2, okay? But I want you to, let's kind of take a step back for a minute, okay? And so I want you to remember that W of X, right? So this was our weighting function. And so even though, we used it to reduce the derivatives in our problem, we don't actually care what W of X is, okay? In other words, it's an arbitrary function. Okay. And so for an arbitrary function, b1 and b2 can literally be anything. So it can be, 50 bajillion, or it can be -4, or it can be 24, right? So it can be anything, and we won't care because it's an arbitrary function. So the only thing we use w of x for was just to kind of, balance the derivatives out in our expression. Okay. And so in this formula that we have on the previous page, I've set it up like this because, if b1 and b2 can be anything, right? Then in order to actually satisfy the equation, the terms in parentheses here have to satisfy the equation, okay? And so what that tells us is that both of these quantities that I've boxed in red, these have to satisfy our equation, okay? And so an equation here was that, this whole quantity is equal to 0. And so in order for that to be, both the quantities in the red here have to be 0. Okay. And so what that's going to give us is actually a system of two equations for two unknowns. Okay. And so if we write it out, we have 5a1 plus 25a2 is equal to 31.25. Okay. We have 25a1 plus 500 over 3 a2, okay, this is equal to 125, okay? And so we have a linear system. So you can actually put this in matrix form. Right? You thought you escaped it, but linear forms will come and find you, always. Okay. Thankfully, it's only a 2 by 2, so it's not as scary yet. Okay, so they're going to get much scarier, trust me. Okay. And then if you plug this into MATLAB, you can solve for the coefficients. So we have a1 is going to be equal to 10, and then a2 is equal to minus 0.75. Okay. And so if we plug those coefficients, we can solve for our approximate solution for t. Okay. And so we have t approx of x is equal to 10x minus 10x minus 0.75 x squared plus 25. Okay. Isn't it 5 instead of 2? Yes, it's 5. Yeah, sorry. I don't know where I got that 2. Thank you. Okay. Okay. And so this is our approximate solution. So actually, let's compare it to our exact solution. Okay. And so this is what we solved for in the first example. We got minus x to the 4th all over 60 plus 25 over 3x plus 25. Okay. And you can see that they're different, right? And so our approximate solution, even though we did all this work for it, it's not going to be the same thing as our exact. Okay. Okay. And so if you actually compute the residual, okay, so remember we defined the residual from before, right? And so we can compute the residual for this to kind of quantify the error in our solution, okay? And I'm going to rush a little bit just because we're out of time, okay? And this is for the approximate solution. Okay. And so if we do that, our residual in this case is r of x is equal to d dx of ka dt approx dt, or dx, sorry. Okay. Plus s of x. Okay. And then we plug in our t approx here, and then what we get as our residual is x squared over 5, okay, minus 1.5, okay. And so if we plot this function, that's going to give us our error, okay. And so actually, another way to see the differences between the approximate and the exact is simply to plot it out, okay? And so let's say that our exact solution is given in the red right here, okay? Okay. But then if we plot our approximate solution on top of it, it might look something like this. So you can see, when we plot them on top of each other, they're close. But because our approximate solution doesn't have our fourth order polynomial, they're going to be different from each other. Okay. Right. And so that's why we give it the name approximate, because they're not going to be exact. Okay. And so you're probably wondering, why do we go through all this trouble to get a solution if it's not going to be exact? Well, this process of finding an approximate solution will really help us out in situations where we can't find the exact solution, right? So you can imagine in 2D and 3D, it becomes a lot more difficult to solve our differential equation for the exact solution. So actually in those cases, if we assume a form of the solution, solve an approximate one, this is going to be a million times easier. And that's the whole idea with the finite element. Okay. All right, any final questions on this before we sign off for the week? Okay. So that's all I got for you guys this week. So thank you everyone for tuning in. I apologize for going over a little bit. And so, on Monday, we're going to learn about finite element forms. So we're going to take the next step for this, right? And so, have a great weekend. If you have questions on the activity, which is due Sunday, then definitely, don't be afraid to reach out. So I have a minute paper that's up on the Canvas site too. So please take a look. And so it's a little bit of a different minute paper this week because since we're at the midpoint of the semester, I kind of want to check in with you guys just to see, how this class is going for you, and anything that I can do to kind of make the second half better than the first half. Okay. So if you have time, definitely check out the minute paper and fill it out. I definitely greatly appreciate it. But besides that or any of that, have a great weekend, and I'll see you guys on Monday. So the midterms I expect will be graded by tomorrow. Yeah, so I had planned to get it done by today, but I had kind of a lot of stuff kind of happen today. So I apologize for that. So usually I try to finish grading, a week after you guys finish the exam. By tomorrow for sure I'll have them graded because I got a lot of the stuff out of it.